Let's continue to upgrade this machine. At the end of my last video, I showed you how this machine was able to mill these square brackets out of aluminum quite easily. But when I take a look again at my design, I realized that I made a mistake here on the Z-axis gantry plate. The holes to install those bolts on this plate was 7mm, not 6mm as it's supposed to be. So the angle of the spindle is actually not square. And I think that on this machine right now, the weakest point is actually this plate. It's made out of plywood, so it might flex a little bit. What I will do now, before I upgrade all the bracket to aluminum, I will upgrade this plate. But I already intend to change the spindle later, so I don't want to use like really thick plate of aluminum to make this. So I will try to do something really cheap. What I decide to do is to prepare one piece of plywood, half of an inch thick, two pieces of aluminum sheet, 1/8 of an inch thick. They should be around the size of this plate. And because I don't want to spend too much time to cut the outline of this plate, I will only use this machine to make all the holes on this plate. And when I attach this plate on the machine, I will do the sandwich like this. So that will make the total thickness about 3/4 of an inch. I think that it will be very sturdy. So let me just cut all the holes very quickly. That was burning a little bit, but everything's still okay. All the pieces are done cutting. Time to reinforce this plate. And that's it for upgrading this plate. The next step is continuing making all the aluminum brackets. But the aluminum bracket is pretty much permanent, I don't want to change them. And also I wanted to increase the sturdiness of the frame, such as these two bars here, and also this bar, because I know that the spindle to mill steel will be a lot heavier compared to this one. So let me just do that on the computer first before making all the brackets. Here's my updated design with all the aluminum brackets and plates. I didn't do any change to the overall structure of the machine. I only add a few more bars to increase the sturdiness of the structures. For example, the most important place I think is these bars here, because these bars will have to take up the whole weight of the Z-axis setup, and also the pushing back and forth, up and down of the Z-axis, so they will need to be very strong and doesn't flex too much or not at all. So instead of having one bar, I increase the number to 3 bars on this. And also to prevent this bar from flexing back and forth, I install this bar at the back with the 2 short bar as a bridge. They will reinforce this bar a little bit. The same with the top of the frame here. Those bars will reinforce the top of the Z-axis block, prevent the top from flexing back and forth. And because I increase the weight of this block, I will have to increase also the sturdiness of the side of the frame. Like this bar here, instead of 1 I put 2. And to prevent those bars from slipping down, I will install 4 of these short bars at 4 corners. So this bar will rest on the end of those bars. And that's it. I think that will be enough. So the first step, I will try to mill all the thin aluminum brackets. After finishing all the square brackets that I showed you last time, I will moving on to the corner brackets. To cool down the bit when cutting and also clearing the aluminum chip, I installed this spraying nozzle to blow compressed air to the bit. And in the future, if needed, I can also mix in some coolant. The good thing about this setup is that this nozzle doesn't need to move with the Z-axis. It can stay in one place, and you only need to adjust the tip to be spraying at the bit. So that is really convenient. So let's see how it cuts with this. I try to go a bit crazy with the 2D contour, 1mm step down. That was way too much, so I will change it to 0.5mm. After reduce the step down of the 2D contour to 0.5mm, everything will cut correctly, a lot less chattering. One thing that I learned now from cutting this piece of aluminum sheet, that the sheet is not completely flat. Where it's not pressed down to the platform, it will vibrate a lot and create the chattering on the bit. I'm not sure how I can do it, but to reduce chattering, make sure that you press the piece down. It only took 47 minutes to mill 4 of this piece. I will continue to mill all of the thin brackets, and then when it gets to the thicker one, I will show you again. I think that I am done milling all the thin pieces. At the beginning I thought that I mill few pieces at the time, replace all the wooden pieces piece by piece to make the frame slowly more sturdy. But then I was too lazy to do that because later on I might need to disassemble everything to install all the thicker pieces and redo all the calibrations. So I decided to mill all the pieces first, then install them on the machine all at a time. Now I will start milling all the thicker aluminum pieces, like this piece to fix the end bearing block and also to mount the stepper motor. I will show you quickly how I will do it. As you can see that I redesigned all the pieces so they all have rectangular shape. This way I don't need to use the 2D contour to cut the piece out of the stock. I will just use my table saw. That will save me a lot of time making those pieces. I will only need to mill all the holes, slot, pockets inside the plate. For all the small holes like this, 4mm, I will only mill a little bit. Then I will use the drill bit to drill all the way through. That also will save me a lot more time. I will show you quickly how I set up the tool path for this piece. Stock. I will choose this corner. 0, 0. Okay. Most of the pieces will be half of an inch thick, with aluminum I think that will be more than sturdy enough. I will go to pocket clearing, select. The holes are 4mm, so I will choose the 1/8 of an inch flat end mill bit. I will reduce this, maybe 600mm per minute. Ram feed rate, I will choose something a bit slower, maybe 400. Plunge rate, I will choose 200. Machining boundary, selection, choose all the small holes inside the boundary. 2, 5 more. This bottom high, I will choose motor topped and go down 5mm. This way I only mill down 5mm. The rest I will use my drill press to drill through. Let's say 1mm step down. Manual step over. I will decrease it 0.5mm. This is to reduce the loading on the bit. Nothing to leave. Shortest path. On 7.5 to be a bit faster. This I will reduce to 0.3mm. Now to the bigger holes and slots, I will choose bigger bit. So I go to pocket clearing, select. $4mm flat end mill. I also will go very slow, 600. Plunge rate, maybe 150. Machining boundary, selection. I will choose the boundary first. To set the inside the boundary. -2, 5, -1.5. This way I will mill all the way through of the plate. Tolerance manual step over. This is very important because the spindle is not very strong. It doesn't have much torque to cut big chip, so you will have to reduce the chip size. So here 0.5mm step over. Maximum roughing step down. You can go 1mm. Nothing to leave. Okay. Shortest path. Here for the ramp, I want to use smooth profile, and I will reduce this to 1 degree so it will go a lot smoother, less chattering. This I can leave it at 1.05mm. Ramp diameter 0.5mm. Click OK. Duplicate this one. Edit it. Choose this big hole. This one, because each path is very long, so I will reduce the loading. Here, maximum step over. I will put 0.4mm. The rest, I don't think that I need to change anything. So I click OK. Now, as I said that I will cut the piece out using the saw, but I still want to have the outline as reference so I can cut more precisely, at least very close to the size that I wanted. So I will do a 2D contour, very shallow. So I go 2D contour. Here, very slow. 250mm per minute. 250, plunge rate 50, very slow. Contour selection, this one. Two. Here, selected contour. No, I actually want to go from motor top. Minus 0.4mm, just a little bit to have the outline. Multi-depth, we will go 0.2mm, so it will cut very smooth. I will use ramp, maybe 1 degree. This I will have to reduce 1mm and click OK. And that's it. I'm done setting up the two parts for this piece. So I will export this one separately and these three together. And I'm done setting up the two parts. Let's see how the machine cut this piece. Here are all the thicker aluminum pieces that I bought. This one is 3/4 of an inch thick, 12 inch wide, 21 inch length. I will use this piece for the platform and also the gantry plate for the Z-axis because I want to prevent that plate from flexing when cutting steel. This set of 5 pieces, half of an inch thick, 4 inch wide, 13 inch length. I think they are more than enough. This piece is about 4.5mm thick. I don't know the exact dimension, but I'm sure that will be more than enough because I only cut 3 small pieces out of this. I will start with one of these pieces. I think that I found a good tactic to use this plate. I will move the stepper motor mount on this side and then I will rotate, flip to the other side and move one of these long plates down here. So I have 3 plates down here that also fit in the width of this plate, and I have 3 stepper motor mounts, so that will be perfect. And also to reduce the number of cut on the saw, when I set the X and Y 0, I will set it right outside of this corner, so when the 2D contour cut, it will only cut the 2 edges in here. That way I only have 2 edges to cut, just a little bit less work for me. So let's get started with the stepper motor mount. This piece will cut exactly as I wanted. The surface is really smooth in here. So I think all the cutting parameters were good. Now I will flip to the other side and mill the longer piece. That is pretty much it. Everything will mill correctly. I will continue to mill all the other pieces, then cut all of them at a time on the table saw. Now I'm done milling with the machine. Time to trim the pieces with the table saw. Just make sure that you keep yourself safe. I have my face mask here. I have this pushing block so I don't cut my finger. For me, it's better cut inside the line rather than outside. That way the piece can be a bit smaller, but not bigger. Smaller, it can always fit inside the design, but bigger, it might not. That's a lot faster compared to cutting with the CNC machine. Now I just switch to this line. I have to say that the outline is not as pretty as cutting with the CNC machine, but that is the trade-off that you have to make to save a lot more time. Now I'm already at the saw. I want to divide this thick piece of aluminum into two pieces. This side will be 12 inch by 12 inch for the platform. The rest will be for the Z-axis gantry plate. The good thing about these two thick big plates that I will only need to mill everything inside. I don't need to cut the outline, and cutting all the holes and slots in here will be exactly the same as I did for the other plates. So I will finish cutting everything with the CNC machine and show you next step at the drill press. Actually, before going to the drill press, let me show you the most interesting thing for me about this upgrade is the spindle setup. What I intended to use for the spindle is this power head. It has 5 bearings in it, so it's very stable and precise. To drive it, I will use this AC motor. Here are the parameters on this motor. 0.5 horsepower. The speed is 2850 RPM. I think that is a lot more suitable to cut steel compared to the high-speed spindle that I have right now. I will need 220 volt to power this motor. And one thing that I think is very important is the duty cycle. This one is continuous, so it will be very good if I need to run a 2-pass that takes a long time to finish. And one thing you might not believe how lucky I was to get this motor. I bought it on eBay for $10 with another $10 for shipping, so it is $20. It's brand new. This power head costs about $180, so in total I have $200 spindle setup. I think that is very reasonable to cut steel. To transmit the power from this motor to this power head, I use these two 5M gears. I will use this type of belt. This one is a bit too long. I'm buying a shorter one. It should come tomorrow. Next step, I will need to make all the holes to install this plate on the Z-axis setup that I have right now, and also all the holes to install this motor, this power head. To do that, I will mark the position of all the holes. Then I will make roughly all the measurement. After that, I will make the 3D model on the computer and cut all the holes and slot with the CNC machine. The same thing with all the other thick aluminum pieces that I will need to finish it on the drill press. Now the drill press for all the plate to mount the end bearing blocks and the stepper motor. I would have to drill through all the small holes here using the 4mm drill bit. Making the M5 thread in those holes are really easy. That way I don't need extra nuts to install the stepper motor and also the end bearing blocks. I have another 5 pieces. Those are the spacer between the linear bearing block and the coolant tray. For the 4 holes in the corners, I will have to drill through with a 5mm drill bit and put the M6 thread in there. Now for the Z-axis gantry plate, these 4 holes here, these 8 holes up here, I would have to make the M8 thread into them. Two hours later, I'm done with this plate, and this $2 Chinese tap is actually pretty good. It's still going very strong after 300 holes. Now I'm officially done with all the plates. Let me just check the design again to see if I need to do anything else. Here is what I found at the hardware store. A piece of aluminum sheet just already bent on the 2 sides. So I would only need to seal the other 2 edges, this one and this one. What I will do with that, I will cut 2 pieces of angled aluminum like this. The lens will fit inside here, and I will bolt these 2 pieces down to the plate, and then I will seal the edge using some silicone. That way the coolant liquid will stay inside the tray and doesn't leak out. With the edges sticking up like this, I can install also some type of fence just like clip on to block the chip from flying out. And when I don't want the fence, I just lift them up, move them away. I think that way is very convenient. Now to the size of this plate. This side is very long, I think 15 inch, much longer than I needed, but I think that would be fine. The extra length can stick at the back and front of the machine. The width of the tray, I would have to trim it to size, about 33 or 34 centimeter. Wider than that, it might bump into the frame of the machine when the X and Y axis move all the way to the limit. So let me just measure the width, trim it with the table saw, mill all the holes inside here, and then I can install it on the machine. I mill all the hole needed on this piece and also trim 2 pieces of angled aluminum. They will fit inside like this. Now I will clamp the angled aluminum to this piece and drill some holes with the 4mm drill bit. Then make the hole a bit bigger on the angled aluminum and make the thread on the tray with the M5 tab. Now I will put the tray together. I prepared 20 pieces of spacer. These are to space between the tray and the platform. Later on, for the coolant liquid to be able to run down to a bucket and be recirculated by a pump, I drilled this hole here, cut in the thread, 1/4 NPT, and I bought this at the hardware store. I will install it like this. I will trim this part off so the liquid can flow down. Next step, I will seal all the edges using silicone coke. I will also seal around the spacers and also the outside of this adapter. And now I only need to wait for the silicone to dry. After that, I will be ready to upgrade the machine. Now it's time to disassemble the machine and replace all the wooden brackets and plates with aluminum ones. Now I take the stepper motor and the end bearing block mount, put on some of the M6 bolt 20mm length and the T-nuts, and I slide the plate on like this. I take 4 of the M5 bolt about 35mm length, slide them through the end bearing blocks and tighten the bolt. Now I can tighten the bolt to fit this plate on the Z-axis block. For the stepper motor, I will replace this small one with this bigger one because the spindle setup get a lot heavier. To fix the stepper motor on this plate, I use 4 of the 40mm length M5 bolt, slide them through here. And the same as before, I will use some of the M6 nuts, slide them on like this as spacers. It feels really heavy already. Now just take one of the thinner end bearing block mount, use some of the M5 bolt, about 20 or 25mm length. Now before working on the X and Y axis, I will disassemble the top of the frame. Now the top of the frame is removed. I will work on the X-axis first. There's nothing really special on the X and Y axis to do. The replacement of the plates will be exactly the same as the Z axis. For the base of the frame, I don't think that I need to replace the brackets at the bottom. I think that the wooden brackets on the bottom will work fine. So I will go through this part really quickly. And that's it, I'm done with the X and Y axis. Now I will rebuild the top of the frame and install the Z axis. My camera wasn't on for the part that I installed the spindle. It was really simple. I only used 4 of the M8 bolts 75mm length and bolt the power head to this plate. And to fit this gear on this shaft, I needed some O-ring to push it down, and that is pretty much it. Now I will install the motor to drive this spindle. Now I have this setup installed, I can turn on the motor just to make sure that it works. Okay, ready, set, go. Everything seems to be working just fine. Now I only need to connect all the stepper motor to the controller board. Then this machine will be ready to go again. Here's how the machine looked like after I put everything together. I haven't finished reinforcing the back of the machine yet, but I really wanted to test how the machine cut. So I will do that first, and if the machine is still really shaky, I will continue with the reinforcement of the frame. As I told you before, I made some clip-on fans like this, that I can remove them very easily. Like this, I will have more space to install the stop, and when I am ready to cut, I can put them back on to prevent the chips and also the cooling liquid from flying outside of the tray. That way it's going to be less messy. For the first test, I don't want to spend too much money to buy a real stock, so I just went to the hardware store and bought this really huge bolt. I will try to do some simple cut on it just to see how the machine performs. I don't really have any experience with steel milling, so I don't know what to expect right now. I just try to go really slow at first and increase the setting later. I hope that these clamps will be sturdy enough for this steel milling experience. I will start by doing a face mill on this bolt using a 12mm flat end mill, 3 flutes. The cut was actually quite smooth. I will try to do the face mill again. This time I will only cut in one direction, so the loading will be the same for every cut and the surface should be even smoother. I did a few test cuts with different parameters, and this 12mm bit chipped a little bit, so I changed the bit to 10mm. I will show you the cut with the parameter that I use right now. 0.5mm step down, 400mm feed rate, and I will use conventional cutting direction. As you can see that it have a tiny bit of vibration, but the cut is actually quite smooth. So I think that it actually not too bad to cut steel like this. After running a few tests, what I found out is that the machine cutting kind of okay. When the cut is sideways, the loading is not too much, a 0.5mm step down, and the feed rate about 400 or 500mm per minute is way faster compared to the 3018 CNC cutting aluminum, but the machine vibrates a lot when it comes to cutting downward. For example, when it ramping down at the beginning of the adaptive clearing. So I think that it will be better if I pre-drill a hole here in the middle and then do the adaptive clearing to bore out the hole. That way it will reduce the loading on the flat end mill and hopefully the cut will be smoother. Few things happened last time when I tried to make a drill on this bolt. When the drill bit start going into the steel, it's kind of plunged down, pulled the Z-axis down, and then it couldn't cut. And I also saw that the Z-axis kind of like very easy to bend back and forth. And also because the Z-axis is so heavy, the coupler on the Z-axis broke, and that also might be the reason that the Z-axis plunged into the steel. So I bought this type of coupler from Amazon to replace this coupler. Hopefully it will work better. I also installed a counterweight system. Let me show you. Here are the extra bar to reinforce the back of the Z-axis. Here's the cable that attached to the weight at the back of the machine. I drill one hole on each side of this plate, cut the thread into the hole, put the bolt in, and I use this type of cable with a loop right around the bolt. The weight on this is about 20 pounds, so about 9 kilograms. And with the counterweight system, the Z-axis can move a lot smoother and faster now. Now I will try to mill this bolt again. I will start by flattening this surface. This time I only cut at 300mm per minute for feed rate. I will start with 0.5mm step down, then I will try 0.75mm step down, and so on to see when the machine starts rumbling. Then I will know the limit of this spindle setup. The step over for the face mill is 4mm. from 5mm, cutting in the X direction is pretty smooth. I will try the Y direction to see if the machine is weaker in this way. Cutting this way, I think there's a bit more vibration, so I will try to cut in this way first. The surface here is actually quite smooth, so I will try to cut at 0.75mm. If it is rougher, I think that will be the limit of the machine. I think that it makes a bit more noise when cutting, but the surface is about the same, so I will try 1mm step down just to see how it will be. One millimeter step down seems to have a lot of vibration, so I stop it in the middle. I will stick with 0.75 or 0.5mm, probably 0.5mm to be safe. Now I will use one of the adaptive clearing parts to trim this down. I think that the cut was pretty smooth. The surface is very nice. But there's a thin piece that still stay in the middle. I'm not sure why. My suspicion is that the tool diameter is not very exact at 10 millimeter. So I take the caliper and measure it. It is about 9.94. So I put that diameter in Fusion 360. Let's run the cut again and to see if this piece go away. The position of the coolant hose bothers me a little bit. It keeps shifting. So I will try to move the hose to a new position so I don't need to keep adjusting it. After thinking about the pictures were left here on the board, I'm ready to admit that some of the comments from viewers on my previous videos were right, that the aluminum frame were not rigid enough. So when the machine cut sideways, the tip of the bit wouldn't step over enough like the setup. So it left a little bit in the center, and I think that was the case. So this structure is not really sturdy enough for steel milling. Because of that reason, I won't share this design. I will try to make another design that is more sturdy and share that. At least I learned something from building this machine, is that the spindle setup actually worked quite well. The cut was quite smooth, so it's actually a good sign. For the next design, I will keep the X and Y axis set up, also the Z axis. I will only need to change the top of the frame to make sure that it's really sturdy and rigid.